In this section, this is where we're going to start with actual applications. To begin with those, we need to set this step function that's used in most applications, and we'll talk about what that means later on. For now, we just want to get the mathematical theory out of it. And this unit step function is called Heaviside function. And this is all it does. It says, they really use this notation in this book, but in other books they use this, which I think is better. So I'm going to go back and forth until we get the hang of this. All what it says, if this C right here is, if this T is less than that C, then it's really 0. And if that T is bigger than or equal to that C, then that's a 1. That's it. So it's either 0 or 1. Either the switch is off or on. So assume C is right there, and this is the T axis, and this is the U axis. So as long as T is less than, let me color code those. As long as T is less than, then guess what? That right there is always 0. And by the time I hit T and C are balanced out, the system turns on forever until you shut it down again. Something we gotta get used to. It's not that bad to get used to, but it takes a bit of practice, so I made few examples for us to really see it. One tricky part, the author assumes after a while you really see U of 0, so they don't write U of 0, they just write U. I'll talk about what that means in a minute. So what this means, this is the key. If T is less than 0, this system is off. Once T hits 0 or more, this system turns on. So if I stick with the coloring from 0 and to the left, this is going to be 0 all the time. And once I hit 0, this system turns on, and it's going to stay like that until you shut it down again. Assuming this is T and this is U. If I looked at, let's say, U2, U sub 2 of T. This is a system that's going to turn on at 2 or off at 2. As long as you didn't hit 2 yet, this is going to be 0. So let's assume this is 1 and this is 2. So as long as you are beneath 2, you could put an arrow, but that really doesn't matter much because the system's off. Once you hit 2, this system becomes a 1. And they chose 1 for a very good reason, because 1 is a unique number. You multiply it by any quantity, you get the quantity back. And you'll know what that means in a minute. Let me do a couple more just to make sure we're kind of comfortable with this. It takes a bit of practice. And if I look at U3 of T, that is basically, the cutoff, of course, is 3. Oops, I got it backwards. And it's a 0 or a 1 non-stop. So, if I take 3, 1, 2, 3, this system is off. It was dormant. Once I hit 3, that is T. I keep on forgetting that. And that is U. I'm going to hit 1. And it's going to run all the way to the right. And here comes the tricky part. If I take U2 of T. U2 of T, I already know what that looked like. I already know 1, 2. This system turns on at 2. Right? And it should run on forever. Minus U3 at T. Well, let's see. What does U3 is? U3 is 0 as long as you are to the left of 3. So 3 is the cutoff. At 3 is the cutoff. So to the left it's 0, but there's already a 1 there. What happens when I hit 3? Doesn't that become a 1, but times a negative, that's a negative 1? Those will undo each other at 3. And the system is shut back down. So it actually looks like this. This system is turned on from 2 minutes to 3 minutes, or 2 seconds to 3 seconds, and it's shut back down. Again, if you look at what this means, this is 0 to the left. We got that. That's not a problem. But it's 1 from 2 and on. So it's 1 from 2 and on. This system is right there. If you put a negative in front of it, that becomes a 0. Well, there's a 1 minus 0, that's 1. But when you get to 3, that becomes, instead of 1, since you're multiplying that by a negative 1, that becomes a negative 1, and 1 minus 1 cancels out. And that's really what you need to get out of the way. Not to worry, we are going to practice this a lot more. I made tons of examples for us to really get this out of the way. A bit more than what the author talks about. This is a very important section. So the graph y equals sine of t, that's simple. We know that y runs up between 1 and negative 1. A sine wave starts at the origin. Of course, this graph is infinite. I'm just mimicking one period, just so that we could see it. This is 2 pi. This is pi. This is pi over 2, and this is 3 pi over 2. So, if I really take this function, this is f of t, and I tag a u1 of t, what does that mean? Well, u1 of t, we are familiar with that. u1 of t is simply, if t is less than 1, if t is less than 1, that's a 0. So 1 and to the left, that's going to be a 0. And t bigger than or equal to 1, it's a 1. So it's going to only start at 1. Well, what does that mean? Well, let's see. I'm going to take this graph. Probably you're better off starting this way. You're better off going in and saying, you know what, I'm going to take this graph that I have. The graph looks like this. That's the 2 pi. That is the pi. That is, I wrote that as a 1. I keep on packing things. Okay. I'm going to use that as pi over 2. And that is 3 pi over 2. So this is the graph of this function. By multiplying by 0, so pi over 2 is 1.57. 1 is about right there. So what this is going to do, this is going to zero out everything to the left of that 1. And guess what? You're going to be left with, there, perfect. It's going to zero out everything to the left. And you're going to really have a portion of, 1. Versus u1 f of t, remember, based on what I wrote it, that's u of t1 f of t minus 1. What this does, this shifts the graph. If you take the sine of t minus 1, doesn't that take this graph and shift it 1 unit to the right? Everything's off now. So there's a massive difference between me shifting the whole curve. This will be 2 pi plus 1. This will be pi plus 1. This will be pi over 2 plus 1. And this will be 3 pi over 2 plus 1. So there is a massive difference. And of course to the left it is 0. There's a massive difference if I shifted or if I just multiplied. And that's something we're gonna play with. And let me start now officially with the problem in the book and start talking about how this works. So first things first, I need to figure out what this graph looks like. The graph of y equal t squared, I know how that graph looks like, roughly something like this. And let's see how this works. F of t, there's f of t. When they say f of minus t, f of t minus pi, and u of pi, that means they shifted this graph. It's a translation. They picked this graph up and they shifted that pi units to the right, the other side, your other right. So if you go to pi 3.14, assume it's right there. And what you're gonna do, you're gonna really look at u of pi. Well, let's see. U pi of t is actually, if t is less than pi, it's a 0. There's nothing to the left. Again, it's going to take some time for you to get used to this. That's normal. That's what I'm doing right now, and that's why I'm giving you tons of homework to get that right. And if you look to the right of pi, that's a 1. Since you're multiplying those and it's shifted, then to the right, it's going to look like this. Versus, when I added, again, I want to make sure you really see this solid. Versus, let's call L of t to be f of t times u pi of t. What's the difference between those? Well, the difference here is that this function is actually t squared. So it looks like this, really. And here, it looks like t minus pi squared u pi of t. So if the shift matches, you just translate the graph. You pick it up and you move it that many units. Remember, to the left, it's always 0. If you multiply, if this t doesn't match that shift, what it does, it's kind of like you looking at this graph, kind of, right? And what this does, this is going to be to the left, assume pi is right there, right? To the left of pi, it's going to zero out all of that. So basically, it's going to erase all of that part, eliminating a portion of the graph, and the only piece that will remain will be this part only. So there's a big difference between me shifting and between me eliminating. That makes a massive difference. And let's look at number 4. Of course, this part on the right is all extra. This is all they wanted. Let's look at number 4 and see if we can make sense out of this. And let's see how this goes. I look at how this plays. I'm looking at g of t equals. It seems this system, to the left of 1, it's always 0. There's nothing there. Okay, that is for certain, right? Now, to the left of 1. And at 1, when I get t to be 1, this system turns on, giving me t minus 1. Right? But it runs on until 2. Until 2, this other system turns on. Now, what happens from 2, and I know this coming system is going to run till 3. This system turns on. So, this system was on and this added to it. Now, the result here is going to be the t minus 1. And since this other system turned on, minus 2t plus 2. That makes a net result of negative t plus 1. And what happens when t is bigger than or equal to 3? This third system turns on. So you add to this t minus 3, or simply add to this t minus 3. And that will be t minus 2, if I'm not mistaken. And that would be it. Oh, time out. Yeah, that is 2t plus 4. That makes this plus 3. My mistake. Oh boy. Okay, let me fix that. So when this system turns on at 2, now you have t minus 1 and negative 2t plus 4. That makes it negative t plus 3. There we go. So now I am at negative t plus 3. And when this system turns on at 3, I'm going to add to this at t minus 3. That will make it t minus t is 0, negative 3 plus 3 is 0. So how does this look graphically? If I go to 1, to the left of 1, it's all 0. So there's nothing there. And do I know how to graph t minus 1? Well, yeah, if you put 1 in there, you get a 0. And if you put 2 in there, you get a 1. And do I know how to graph this? Well, yeah, put a 2 in there. When x equal 2, y equal 1. So this, the green is really open, but the blue is already going to fill it in. And when you put 3 in there, you get a 0. And by the way, this is not always going to 0 out, but this is how these applications work. And what happens to the right of 3? That's going to be 0 forever. Okay, let's look at the next problem. If I wanted to talk about the following system, and let me color code those. And this is really simple in the sense they're only numbers, but they could be functions. Let's look at all of these and see really what is happening with those. Part A, sketch the graph. Well, let's see. To the left of 0, so this system, to the left of 0, it's simple. It's always 0. Normally they leave that out. Normally you really don't even fill that out. You just leave it blank, but it doesn't matter. This system turns on at 0 to 1. At 0 to 1, this is 1. So it starts... Oh, I messed up. That's okay. I do that a lot. That should be... that should be excluded. There we go. So this should be excluded. And here, this is a 1. And then what happens? When this system turns on, and this system turns on from 1 to 2, do you see that 1 is already there? When you add negative 1, isn't that a 0? And it runs to 2. What happens at 2? At 2, the blue turns on. Well, 1 minus 1 plus 1 is actually 1 again. All the way to 3. At 3, this turns on, and if you add those, isn't that a 0? And that runs to 4. And then, this really doesn't add much. It just picks up and continues on from 4 to infinity. If I want to write this out, and this is something that you really need to get out of the way, f of t equal. So this system, this is the part the book doesn't write. I'm going to say this system turns on at 0. So this book says u0 of t. I'm going to tag that in front of it. And this system remains, right? It remains 1. And when I get to 2, when I get to 1, so this is u of 0. To the left of 0, that's zeroing out. Now, do you notice that do you notice that I am gonna get at 1, I am gonna get a negative 1? If I already have 1, how do I get a negative 1? Remember, when this system turns on, those two gets added. Shouldn't that be a negative 2? If you add those, you'll get the negative 1. So that's the red system. Now, when the blue turns on, that blue turns on at 2. I already have 1 minus 2, which is a negative 1. I want to go to 1. I am at negative 1. I want to go to 1. How do you go from negative 1 to 1? Don't you add a 2? And when I get to the purple system, it turns on at 3. Again, this is a must. I am at negative 2 plus 2 is 0, plus 1. So far, I have a 1. But I want the outcome to be a negative 1. What do you put in there so that when you add to 1 to get a negative 1, you add a negative 2? And the last system turns on at 4. And I have a negative 2 plus 2, which is 0, a negative 2 plus 1, which is negative 1. How am I going to make the outcome of those a 0? If I have a negative 1 already, don't you just tag a 1? And there it is. Again, something to practice on. And we're going to do that again before I conclude this video and move to the next video. So another problem just like this, let's do that as well. This system looks like y equal t. Y equal t turns on at 0. So part A, at 0 you turn the system on. To the left, you really could ignore that. That's just a 0, right? Or you could just start at 0. It doesn't matter. At 0, the system turns on. Y equal t. So 0, 0. If you put a 2 in there, you get 2. When I get to 2, y equal 2 is a horizontal line, right? So that stays at 2 all the way to 5. And at 5, what happens? At 5, this system turns on. And what would happen then? If I throw a 5 in there, at 5, 7 minus 5 is 2. And if you put a 7, isn't that a 0? And what happens to the right of that? What color have I not used yet? That one. And once you hit 7 or bigger, it's going to be, it's zeroing out. That's part A. Part B is, I don't want to say as important, I really want to say more important than part A. So how does that work? This system starts at 0. And at 0, what do I have? T. Plus, at 2, this second system turns on. And I want the overall to be at 2. I was at T, and I want to do something to it and get it to be at 2. Wouldn't that be negative T plus 2 if you add a negative T plus 2? Doesn't that give you a 2? So now I know up to here this system is at 2. The blue turns on at 3. And I want the outcome. I want to add something to this and get it to be 7 minus t. What do you add to 5 to make it... Okay, you know what I'm thinking. What do you add to 2 to make it a 7? So you should add a 5 minus t. This is what I have right now. And when the 7... that wasn't 3, that was 5. You guys say something. Wasn't that at 5? And what happens at 7? At 7, this system turns on, and it seems we want the outcome to be a 0. if this is what I have, I want to, oh boy, okay, this is really annoying. This key is in my way. Every time I touch it, things shift. Here we go. What do I add to this to make it a 0? Wouldn't that be a -7 and a plus t, or t minus 7? It's crucial that you get this because that's really where the application is. Now I'm going to conclude this video and continue this in the next video. I'm planning to do, I can do all the events. I really need you to get very comfortable with this.